All right, let's go ahead and get started. If you have any questions, throw them into the chat, and I will take a look at them. As I notice them. All right. Last time we started to talk about the process of creating integration tests or system level tests, where you look at combinations of features and how they work together to perform the overall high-level tasks of the system, generally accessed through a defined interface, through an API, through a user interface or a graphical interface, through a command line interface, through some kind of defined interface. And as we talked about last class, this is generally a 5-stage process, where first you identify what are called the independently testable pieces of functionality surfaced by that interface of a subsystem or of your system as a whole. So what are the features or what are the functions that are surfaced by an interface and can be tested in relative isolation? What are the things that, working through this interface, we can make the software do as part of our interaction with it? Now, for each of those pieces of independently testable functionality, we take a look at them one at a time and design a series of test cases for them. And for each of those, what we need to look at is what varies and what do we have control over when we're testing that particular piece of functionality. And that includes, of course, the concrete input parameters to it, what kind of information you pass to that functionality, but more fundamentally, what kind of choices do you make when you execute that functionality? And the product line, that includes the variation points, where you choose from a set of features that affect that functionality, and those choices in turn affect other choices. This also includes implicit input, like environmental factors, your networking environment, your hardware environment, the contents of your database or the contents of records that you load, that can in turn affect the outcome of that functionality when you test it. Now, then, for each of those choices that you make, look at what are your options for those choices? What are the things that you choose among when you make that decision? So for the product line, for a variation point, what are the features that fill that variation point? Those are your choices for that, your options for that particular choice, right? Often you divide this up for concrete input, for not for your product line, but for something where you would fill in like an integer value or a record of some kind. And you try and divide up the input space into the different outcomes that can occur. And then you combine those options to form a series of what are called test case specifications or test recipes. These are abstract test cases that you could then instantiate using concrete values and run one or more of those sets of concrete values against the system at the end. Now, this process is going to leave you with a lot of these test recipes, and each of those abstract descriptions of test cases can be instantiated with often many different concrete instantiations, right? And that can lead to hundreds of concrete test cases for one high-level function of your software, and you're not going to write and test every single one of those, right? So you're not even going to have necessarily one concrete test case for every possible one of those test recipes, every one of those test specifications. You just don't have time for that, right? So what is important? What should you do? What are the important feature interactions to focus on? And which of those should you instantiate as concrete system level test cases? And that's something we're going to explore today. So in short, what we're going to look at is how you can filter this list of test specifications to capture the important cases, to capture the ones that can lead to errors or the normal execution, and then filter out impossible or redundant combinations of values. And then in the second approach to this, what we're going to do is try to capture different pairs, two-way interactions between different features. Rather than trying to cover every possible combination of representative values, rather we're going to look at these two-way combinations of values, cover all of those, and then in a far smaller set of test cases, basically identify almost all of the important execution scenarios. So a key focus of this course has been on building customizable, feature-rich systems. And we've talked about making features explicit in design and in code by separating and modularizing our feature code. But a feature doesn't exist in a vacuum. Features interact in various ways, both in positive and intended ways, but also in critical and unplanned ways, right? So features are often expected to interact with each other. And most of what we talk about are features that exist on their own, and then we plug them in. But features are expected to interact. They exchange information, they determine the behavior of other features, they reuse the functionality of other features, and they accomplish tasks in cooperation with each other. But inadvertent interactions can cause all sorts of unexpected or incorrect behaviors. And detecting and resolving unintended feature interactions is a key challenge in developing a complex system versus a less complex system. In all these cases, you'll test the individual elements and make sure they work. But in the product lines and complex and feature-rich and reuse-driven systems like we've been talking about this entire course, the interactions are often go horribly wrong. So detecting and resolving unintended feature interactions is one of the key challenges here. And so we want to design our test cases to examine critically important feature interactions and have a high chance of detecting those interactions. So basically, that's today's goals. How can feature interactions create faults, and how can we just choose the important test cases to give us a slightly higher chance of detecting the horrible feature interactions that could go dramatically wrong and make everything go skidding to a halt, right? So a feature that works perfectly well in isolation can exhibit behavior that you don't expect when it's combined with other features. And the problem here is that when features are developed independently, it's difficult to predict their mutual interactions when they're combined, right? So when we're performing domain engineering and we develop these reusable assets that we plug in, those we're definitely going to test. We're going to test those thoroughly in isolation, but we don't necessarily know what's going to happen once we start combining these different features together in a concrete product. Typically, the behavior of the complete product that contains multiple independently developed features is not something we can easily predict from understanding each feature on its own. What we need to do is identify and understand their interactions during system level during this integration testing phase. So a feature interaction between two or more features is an emergent behavior that cannot be easily deduced, easily figured out from the behaviors that we associate with the individual features involved. An inadvertent feature interaction occurs when one feature influences the behavior of another unrelated feature in an unexpected way because they happen to exist in the configuration together and they interact in some form. So, for example, maybe it took an unexpected execution path in the code when they're combined, or maybe you got some kind of unexpected output or program state, or some change in timing, or some other visible change in the behavior of the program because these features are interacting with each other in a way we didn't expect. When features are combined, their interaction with each other needs to be coordinated. For example, you need to be careful in how you order their execution, how you synchronize data access between them. So even if they don't call each other, maybe they work with the same core data. You need to define precedence rules for who gets to take an action, when, and in what order, who gets top priority. And you need to look at missing behavior and what happens if, for example, you try to select a feature that doesn't exist yet, but your code's set up to allow it. So the feature interaction problem when we talk about this is to detect, manage, and resolve these unplanned, these inadvertent feature interactions. So let's give some examples of this. For one example, you can consider what's called fire and flood control. So in a building automation system, you have a feature called fire control, and they can activate the sprinklers when the sensors detect a fire, right? And in your automation software, you also have a feature called flood control. And flood control is going to cut off the water supply when it detects water on the floor. For instance, this way, if a pipe bursts and your room's getting flooded, this home automation system can know, hey, I'm going to cut off the water if I sense too much water flooding into the room. Individually, these are both great features, and they might operate as we'd expect. Like we've set up our software, we do some simulation, we verify that the flood control kicks in when the water sensor goes off, and the sprinklers go off when the smoke alarm goes off, right? But they might interact in inadvertent ways that you didn't really think of when you were planning these features independently. You can probably already imagine how this goes, right? So when a fire is detected, the fire control is going to activate the sprinklers. But once that started to go for a few minutes and some water is building up on the floor, well, what if your flood control detects standing water in the room and turns off the water main? And now, as a result, your building burns down. So clearly, there's a potential inadvertent interaction in place between fire control and flood control. And we don't want that to happen. And we want to control this home automation system so that if there is a fire, we don't cut off the water, right? We just let that water come in because it's better the room gets flooded than the whole building burns down. And this is inadvertent in the sense it's hard to predict when planning, and it's hard to predict when implementing those features independently. But once you understand that this can happen, you can take corresponding steps to manage or resolve the situation. For example, you can give priority to the fire control feature over the flood control feature, controlled by some kind of coordination code in your home automation system. Or consider, this is a real scenario that happens with WordPress plugins. There we go. WordPress plugins, right? So you can, in the WordPress blogging system, you can install different plugins that add additional functionality. And we have a plugin in place that turns symbols into emojis automatically. So you do colon and right paren, and that becomes a smiley face. Great. But we also have a plugin in place that inserts a forecast widget into the posts, which is activated when in our post we type, this open square bracket, colon, weather, colon, close square bracket, right? And that's going to insert a weather plugin. Well, again, you might see the problem here. This end bit, right? This colon and the closing bracket. Well, that's also a type of smiley face, right? That's also an emoji. So in isolation, each of these features works just fine. They do the correct substitution when you post your blog post, and it works well. Each has been fully tested and works as expected, but when we combine them, we get the unexpected behavior, where suddenly, instead of inserting the weather widget, we get this closing smiley face, right? Or we get the little smiley face with little sunglasses. That's not what we were hoping for. We were hoping to see the weather, right? This breaks the weather plugin because the emoji plugin is activated first and sees this smiley face and inserts your emoji. If the ordering were reversed, it worked just fine. However, the two plugins were developed independently and they weren't tested together. Well, why would they be? They were probably developed by entirely different people. So as a result, we get an unexpected interaction. And really, to resolve this, what we need some control over the ordering that plugins are activated. And this is a meme-heavy class today, right? So again, we see some feature interactions going on here. These illustrate pretty succinctly how features can interact in unexpected ways, even after you test each in isolation. So on the left here, we have a perfectly functional door lock on a perfectly functional sliding door. Each of those, a lock and a sliding door, great. In isolation, fine, but combined, that lock doesn't do a bit of good, right? On the right, we have two windows. Turn the knob, pull it, and it opens. That would be great if you had one or the other, but in combination, they block each other. And that illustrates why unit testing is critically important. It's important each of these features work really well on its own, but it also illustrates why interaction or integration testing is so important. Unit testing will completely miss how these features interact, whereas integration testing will detect these problems. And these examples kind of show us the breadth of possible feature interactions. Some feature interactions are undesired and inadvertent in the sense they're hard to predict when planning and implementing features in isolation. Other interactions are desired and they're planned in advance and are great. In any case, features need to be coordinated more or less explicitly, and that may require some additional coordination code to make them work together, to define things like precedence rules so that the WordPress situation is resolved or the fire and flood control are resolved. This also means feature interactions may harm feature modularity, right? The independence of features. Because besides the fact that each feature has its own code, there's also code you need that doesn't belong to a single feature, but that coordinates the interaction, that belongs to the combination of features, right? And that can make it harder to design these fully evolvable, fully changeable systems. It's something you need to be aware of. All the examples so far illustrate interaction between pairs of features. And when we talk about this compromise between the fact that you can't test everything, you need to test something, and you want to get good results, we're often focused on two-way interactions or first order or pairwise interactions, right? And we try to cover different two-way interactions between items. So let's say we had features A, B, and C, right? Well, what we really often focus on are A and B, A and C, B and C, and how they can interact with each other. Now, that's not all we can do, though, right? And A, B, and C together might also interact in ways we don't expect. And that's what's called a three-way interaction or a second-order interaction. And that's something that we may want to detect, but it's usually a slightly lower priority. Often the focus is on pairwise interactions, but maybe we care about more and more three-way interactions, four-way interactions, and so on. This can be extended into even higher numbers of features. So if n features interact, but none of their strict subsets, that's called an n-way interaction. So higher order interactions, more than two-way, are hard to illustrate in small examples. They usually emerge from complex combinations of features. But here we've got some stat code that's implemented using preprocessor directives, right? And so we have three features: locking, logging, and undo. The code that coordinates the features of the stack is implemented as nested preprocessor directives. So we have these three features, and there's code that belongs to each of the individual features, right? So for instance, lines 36 through 38 are part of, belong to the logging feature. If we enable logging, we'll write this log message, and we see this at a couple of points in here, right? But a lot of this is also nested within other features as well, right? So in this code, we've got three two-way interactions and we have one three-way interaction. And to identify that, well, we need to look at the nesting within this. So for instance, here on line 4, we open some code that's only included if we use the locking feature. That's line 4, and line 12 closes that. Within that, we have a nested preprocessor directive for logging, right? So that's a two-way interaction between locking and logging. We have some code 13 through 15 is just undo. That's great, fine. We have some for logging down here. That's just logging that defines this log method. That's fine. Here, though, we've got undo, and within that, locking for 25 through 33 is locking, and within that, logging. So that's a three-way interaction right here, right, between undo, locking, and logging. You need to watch out for these a little bit. These can be very tricky, and if things go wrong, like if line 29, for instance, if that for some reason caused an issue, like it threw a null pointer exception, this failure would only occur in products with all three features selected, but not in products that select only a strict subset of those features. Now, higher order interactions, third way or more, do occur in practice. They can be very severe, but they're rare compared to interactions between pairs of features. So like we said, we're usually focused on two-way interactions and trying to make sure that we test those fairly thoroughly. All right, so how do we select the right feature interactions when we're testing? Well, there's two techniques we're going to cover, which are complementary. You can combine these techniques really in either order you want. But the first is what's called the category partition method. And this is just a simple extension on the exact process we talked about last class of where we've gone through, we've identified our testable features. We identify for each of those the choices we make when testing, and for each of those choices, we identify representative options and then form test specifications from there, right? So category partition method is a method of generating your list of test specifications, those abstract recipes. And it simply adds a small number of additional steps in the process we discussed last class. So for our independently testable function, you identify your choices, your representative values, and then a series of constraints. And the constraints are the new thing, right? So the choices and representative values we talked about last time, what you control when you're testing, and then the options you choose for those choices. The new element here, though, as it says, the constraints, and there's three types of constraints we define called if constraints, error constraints, and single constraints. And what these do is they take the set of specifications you identify and then let you eliminate some of those to get a smaller, more compact set that really covers what's important, right? So this is used to control the number of test case specifications that you need to create concrete test cases for. It lets you determine the number of cases that you'll need to create before you spend the human effort to actually create them, which lets you determine, or which is a powerful concept. If you have too many test cases to make these test specifications, then you can try and come up with more constraints that make sense and then prune this set further down. This is a better approach than building a bunch of tests and then realizing that you covered redundant outcomes and that you're out of time, right? So we start as before, and this is a little bit of review, but it's important to drill down each of these items a little bit. So we start as before by identifying our choices, right? So just like before, you'll identify those high-level functions surfaced through our interface and their parameters, right? The direct input parameters, but also environmental elements and the options we choose in our product line for each of these variation points, right? And then we think about what defines each of these parameters. What do we control when we're testing? So not just do we provide an integer for an integer input, but what can we control about that integer and what kind of effect can that have on the outcome of the test cases? And then what are the different values that make sense? If you read more about category partition methods, so on the schedule page on Canvas, I linked to a couple book chapters from a testing book that I think also help explain this with some more examples. They refer to these as categories. So there's a difference in terminology, but I'm trying to be consistent even though the creators of these different methods use their own words for it, right? But this is also known as categories. So let's talk about an example of this. We have a web shop that we're building that sells custom computers. And on the shop, we form configurations. Those are a set of options chosen for a computer model. So we have a function. Oh, and some of those combinations are invalid, like you choose a DisplayPort-based monitor and your computer is HDMI video output, right? So we have a function we want to test called check configuration that's surfaced by an API. It takes as its direct input a model, and then a model of computer that you want to order, and then the configuration for that you've chosen for that model. And it comes back with a Boolean, or it comes back with a Boolean result that says, hey, this is valid or invalid, right? Now, when we are going to test this, we need to think a little bit. When we're testing this, we don't need to just pick a model and configuration arbitrarily, but rather we should think about what these mean and what we have control over when we test, because those are our choices that we make when designing test cases. It's not just a model and configuration, but we need some information on what defines a valid configuration. And maybe there's a database of models and components that list the options available. Well, that's not a direct input to this function, but that's something that we can control the contents of when we test. And so it's important that we consider that as well. It's required for the code to function, and its contents impact the execution. So then, what can we control? What do we actually need to control when we're testing this? What are our choices? Well, what we can do for one thing is we could look at documentation or requirement specifications or user stories or manuals, any other information we might have lying around that can tell us. And so, for example, for this particular function, we have some documentation, what defines a model and what defines a configuration. Right? Well, okay, fine. So let's look at this. For a model, it identifies a product, it determines constraints on the available components, it has a model number, and it's characterized by a set of slots. Each slot can be required, which means it must be filled with a choice, or optional, where it may be left empty. Great. Now, for a configuration for a model, this is a set of one or more pairs of slot and component. Right, so in slot 1, here's the option we choose. It needs to correspond to the number of required or optional slots for the model. The components, there's a set of available components determined by the model and a default for every slot. So in our information about the model, we can get information about what the default choice is for each slot if you don't choose anything. And slots can be empty, which may be the default for the optional slots, but not the required ones. Components then that you choose for this set of slots also can be compatible or incompatible with a model or with each other. So you might choose a set of options for this where they conflict, even if technically it's you filled the right required slots for the model. All right, so this gives us a lot of information we can work with, and we can think about how the model influences the components. How many slots do we have? Are those required or optional? And are the selected components compatible with those slots? So when we think about this, then we have really maybe three parameters that we have control over when we're testing. We have the model, we have the configuration, and then we also have this implicit one, which is a product database. And then for each of those, what are the things we can control that determine the outcome? Now, there may be a lot more we can control for this, but just to give a few things for this example. Well, for a model, we have the model number that identifies it. And we have the number of required slots, so the slots that must have a component assigned to them. And we have a number of optional slots, which can have a component assigned or be empty. For our second parameter, the configuration, well, we have one thing we can control is whether it's a valid configuration for that model, right? When we go to choose the concrete input later, this can get, we'll have to come up with one that is valid or invalid. But at this high level, we first decide, well, maybe it'll be valid or maybe it'll be invalid. We can choose the number of slots for the configuration that are required and the number that are optional with non-empty selections. Right, so how many of these are filled? How many of these have nothing in them? And then for each of the components we select for each of the required and each of the optional slots, are they valid selections? Valid for the model and valid with each other or not? And then for the product database, maybe we just care about, well, there's some number of models in the database, 0, 1, more than 1, some number of components in that database that we're aware of. And of course, there's a lot more we can do here, right? This can spin out of control quickly. I want to keep this a little compact for the slides, but also just in general, when you're performing this process, you want to be a little bit careful that you can't try everything. So think a little about what is going to capture important outcomes of this functionality, right? And just try to be relatively thorough in how you test this, but make sure you're capturing important scenarios and don't go wild with testing everything you possibly can, because this is one feature of your software, right? You might have many different features that you're surfacing that could have each of those have many different ways you can test it, right? So be careful, but just put a little brainstorming into this and figure out, well, what is likely to go wrong here, right? And capture that. Okay, so again, just like last time, we now want to form our test specifications by coming up with representative values for each of those choices, right? What are our options? We have many values that we could possibly select for each of these choices in this scenario. Especially if these correspond to your input variables for the system, where we may have a near infinite number of possible selections for a choice because we're talking about, the space of all possible components or all strings or all integers or things like that. And so we need to look at each of these choices and consider how to partition those into classes of values that could reach different outcomes of a function, or that represent some kind of logical grouping or logical range for that value, right? And especially for the, we need to look at the outcomes that can occur. We need to especially focus on things like error handling and try input that triggers the error handling code to make sure it works as we'd expect, right? From here, then, we form our test specifications or selection of values for all choices, and create concrete test cases that then fill in values for those abstract recipes. All right, so returning to our example, we have here 3 parameters, and each of those we make different choices. So for the model, we choose the model number, the number of required slots, the number of optional slots. And now we need to drill into this and think about different representative values that we can choose. So for the model number, we've got a valid model, one that's not in the database, and maybe we'll try a malformed model number. So fill in something that, if we expect models to be a 5-digit integer, well, fill in something that's not that, right? Something that isn't what we expect, just to see how it's handled. Do you return the right error or exception, or does it try to process it? Now for the number of required slots, well, we might want to try something with no required slots where everything's optional. Try something with 1 required slot, and try something with just more than 1, right? And that you see this often for things that are numbers like this. Try something that's empty, try something with 1 entry, try something with 2 or more. Same for the optional slots. All right, our second parameter is the product database. We have 2 things we're controlling, the number of models in the database and the number of components in it. And again, here we just have the 0, 1, 2 or more, right? Just to see if something goes wrong when we have 1 item in here or it's empty. And then just the normal scenario where we probably have many different models or many different components. And then we have the configuration. And here we have 5 choices we make. Does the configuration match the model? Well, for this, there's complete correspondence. There might be something where our configuration leaves out slots that are required, something where we add additional slots, or something where the number of required is incorrect or number of optional is incorrect, but maybe the total is correct. So like there's 10 slots in total, and we expect 3 required and 7 optional, and maybe in our test we have 5 required and 5 optional, and we see what happens. Number of empty required slots, they're actually empty. That's a mouthful, but okay. All the required slots are full, or they're all empty, or just some of the required slots are empty in here. Likewise for optional, all the optional ones have something selected, all the optional ones are empty, some of the optional are empty, and that way we can test different processing outcomes. For the required slots, what did we select? Well, maybe they're all valid. Some are their default values. We have some that are incompatible with the slot. We have some that are incompatible with another component, and we have some that aren't in the database. Right, so this again captures the different outcomes we'd expect from testing this particular functionality. And we can do the same thing with the optional slots as well. Ones they're valid, where there's some are default, some are incompatible, and so on. Right. This doesn't capture everything we could possibly do, but again, you're trying to capture normal everyday behavior and some of the exceptional scenarios as well that could go wrong. Right. Think of different ways you could break this. Right. And from here, then, this is where the new elements start to kick in. Right. So as a starting point, what you do is you look at your number of test case specifications, right? And that's all possible combinations of those choices. So if we go back up here, right, you'd choose malformed 0, 0, 0, 0, etc. Then malformed 1, 0, and so on. Malformed 1, 1, and so on, right? You see every possible combination of these. As you can imagine, this is a pretty high number you get. So the base level, the number of possible test specifications is the Cartesian product of the number of representative values for all choices, right? Now, the number of combinations of abstract test specifications is going to grow exponentially as the number of choices and representative values for each of those grows. So for a simple system with 5 choices, 6 values for each, that's 7,776, 6 to the 5 test specifications. That's insane and impractical, right? You're just not going to do that. But we don't need all of those. A lot of those are redundant to each other and aren't going to tell us anything new when we test, right? Many of these might be impossible combinations in the first place. They're values that don't make sense to choose together. And that's where the ideas of these constraints come into play. You want to eliminate any combinations that are impossible, identify constraints that can be used to remove unnecessary combinations, and from the remainder, choose a practical subset to test your system with then, to turn into your concrete test cases. Right? So here, for this example, we had 7 choices with 3 values each, 1 choice with 4 values, and 2 with 5 values, right? And so that gives us 218,700 test specifications. Needless to say, you are never going to do all of that when you're testing one function of your software. And many of those don't correspond to reasonable specifications. For example, it's not reasonable to have a test with a valid model from the database where the database has no entries in it, right? So we can eliminate many of these pairings. There are 3 types of constraints that we can define to reduce that number of pairings. The first are called if constraints, where you might choose a particular value for a choice only if a particular value is chosen for another choice. So if we choose X, then we use value Y here for this other choice. Okay. Error constraints are where we note that choosing this value is going to cause an error to occur regardless of what we choose for the other options, right? So no matter what we choose for other options, choosing this value means that we get an exception or we get a particular outcome that's dictated by making that particular choice. And so we don't need every combination of values for all choices that include this particular value. Just one test with this error-inducing value should be plenty for us. So the third are what are called single constraints. And these are very, very similar to error ones, but are more general purpose, right? This is to indicate values that are special or unusual in some way, but are not going to cause an error. They're just going to, they're still going to lead to a normal outcome. We just want to, or they should, but we want to try them once just to be certain that they work. This is often what you use for your weird corner case situations, your boundary values. For example, if your database has 1 model in it or it has 5 models in it, well, the outcome should be the same if you're choosing a valid or invalid model. It shouldn't matter if there's 1 versus 5. And so, but 1 is a weird boundary condition that we try once just to be sure it works. That's a good prototypical example of this single case, right? We're going to try 1 test where we use this corner case value. It should work, but we don't need to try every possible combination of values in association with that one. Just try it once to be certain, right? And then move on. So to take a simple example, we have a substring function. It takes in a string and an index and returns everything from the start of the string to that index. Right? So for each choice, we have some representative values. So we have a choice of the string length, and we're going to try a string that's length 0, 1, or 2 or more characters. We have a choice for the contents of the string, that it contains letters and numbers, it contains special characters, or it's empty. And we have a choice for the index, something negative value, a value of 0, value of 1, value of more than 1. Ignore those for the second. Those didn't animate properly. So what are some constraints we can try applying? Well, one thing we can look at, there we go. Now that looks correct. Well, one thing we can do is these if constraints, right? So for the if constraints, we first define a property. This we will call this 0 length just for simplicity. So we'll give it a variable name. So this property is true. 0 len is true if we choose the value length of 0 for this choice. Now, this can constrain what we select for other choices. So this will dictate, to some extent, our string contents. If we choose length 0, then we can only choose an empty string, right? Otherwise, it doesn't make sense. You can't have a string of special characters that's length 0. So we note this here, right? So if length is 0, then we can choose empty. Otherwise, we can't choose empty. If length is 1, we can't choose empty. And then we have some not the case here. So we can only choose contains letters and numbers if we don't select length 0 here. And we can choose contains special characters only if length 0 is not chosen. Does that make sense? I hope so. Right. Next, we have these error constraints. So if we choose a negative value for the index, that shouldn't work, right? That should either cause a particular outcome, like it returns nothing, right? Or it should throw an exception. We have some sort of code in place or some plan in place for it. But no matter what you choose for your string contents, if you choose an index value less than 0, it's going to get this outcome. So this is an error case. We're going to have one test case with value less than 0, but we're not going to use any other test cases with that. We don't have to worry about every combination of length 0 and this, length 1 and value less than 0, length greater than 2 and value less than 0. We just care about one time where we try this to make sure we get the error, right? And then the third is that single case. And this is something, here we have this on this contains special characters. This shouldn't result in an error. It should be fine to have a string with special characters. Shouldn't be a problem. But we'll try it once just to make sure nothing weird happens, right? And so we note this was single. We're not going to try every possible combination of other values in this. We're just going to try it once. Make sense? Feel free to ask questions if you have any as we go along. All right, so now we're back to our computer configurations again, and we start out with 218,700 test specifications. That's not something we're going to actually try, right? And so we can apply some constraints to reduce this number. And we can work this down by adding these constraints, right? So first we have error constraints. And as I said, the label error means this is something we're going to try once when combined with other non-error values of other choices. No matter what combination, if we give it an invalid model number, it should fail, right? The system, this is an erroneous case. The system should hopefully handle it properly, but no matter what combination of things we choose with it, it's going to be some kind of erroneous outcome. So if you set this, you get an error. So right off the bat, we're only going to do one test case with this in place. In these error cases, we have some other ones here, right? So we have an error if we have 0 models in the database, that's an error. If we have 0 components in the database, that's an error. If we've left slots out of the configuration that should be there for that model or put extra slots in, those are errors. Or if there's a mismatched number of slots, that's an error. If we've selected components that aren't in the database for either required or optional slots, those are errors, right? So we have 8 error cases. So we're going to write 8 test cases to capture those, and that's it. And then with the remaining choices, we go down from 218,700 specifications to 10,376, right? We have, yeah, all right, so now after we remove these error slots, we've got one variable of one choice, 2 with 3, 3 with 4, 4 with 2. Right? So that has a huge impact right off the bat. It still leaves a large number of test specifications. We're still not going to write 10,376 test cases, but it's a lot better, right? And now we can get this down even further. Right, so next, then we can look at these look at these single constraints rather. These single constraints, as I said, act like an error constraint. It's a situation that's not meant to be an error case. It should still work, but it might be a boundary condition or a rare value or something weird could happen. So we try it once and don't worry about the rest of the time. So these single constraints take us down to 662 from 10,376. That's much more reasonable. And then finally, we have these if constraints and these properties, right? So if we choose many slots, then rs many is true. And we can only choose some required slots empty if this is the choice we make, right? And so that's going to reduce us even further from 662 down to 464. That's still quite a lot, but that's much better than the 218,000 we start with. We can add more constraints if we want, or our next technique, combinatorial interaction testing, is designed to choose an interesting subset from the remainder to cover the important choice interactions. Right. There's a question. So the single constraint is like error, except it's not expected to fail. That's exactly right. You can basically think of this as single are corner case values that should give you the normal functionality, but they could go in weird ways if we didn't handle them properly. This is often boundary conditions between error and non-error cases where you try them once, but they function in the same way. It's just a difference in how you think about them. The error ones are explicitly to check your error handling code to handle situations that don't give you the normal expected execution of this feature. Whereas the single one should give you your normal expected functionality, but something weird could happen, and you want to try it and make sure nothing weird happens. Does that make sense? Right. Are there any other questions on this? All right, so then what I want to do next is a bit of an interactive example. And there's a link here on the slide. This is also listed on the schedule page on Canvas. We have a little activity where we have this find service. It takes in a pattern in a file and it searches, and it'll print out all the times this pattern occurs in the file, right? So if we pass in the file with the word John, it's going to find every time John appears in this file. This also supports spaces, right? So John Smith will find all instances of John Smith. And if you embed quotes in this, as long as you embed the quotes properly, it should find all instances of, in this case, John in quotes space Smith in the file. Okay, so we have two parameters in this pattern and file, and we want to think a little about what we can vary for each of those. So what do we control? And what values can we choose for each choice? And then what constraints can we apply between the choice values, those if, single, and error? So what I'd like to do is we don't have a ton of time, but why don't we take 10 minutes just to try this partially, and then we'll go over one solution to this. Okay, so there's a link in the slide, or like I said, it's also linked. This is the category partition testing activity linked on the schedule page in Canvas. And just take a few minutes to think about this at, let's say about 2:12, then we'll talk about this briefly, and then we'll take a quick break after that. Or if you need a break, you can maybe take a few minutes while working on this. But try this out, and then let's talk about it at 2:12. Thanks, David. I see David pasted the link in the chat too, so you can just click on that. That's useful. I should have done that. Thank you. All right, let's talk about this. I'm imagine you did not quite have time to finish it, so please return to it later on and see if it makes sense to you and let us know if there's questions. But let's go ahead and talk about the solution to it just to make sure we try and cover everything we can today. All right, so we've got this find service, and I should say there's not one solution to this, right? So I've asked you to come up with the things you can control when you're testing. I wouldn't expect that your solution exactly matches mine, right? Because in this case, there's a lot of interpretation to it of what do you think is important when you're testing it. But I'd kind of expected something along similar lines if you think about how you would test this, right? So this is one solution. It won't necessarily match yours, but hopefully there's some overlap in the ideas at play here. So what we have here are 6 things we can control when we're testing. We have the size of the pattern. Is it empty? Right? Does it have one character or more characters? Is it longer than any line in the file? Because those can cause different outcomes. The usage of quoting in this. When we enter our pattern, the whole thing should be in quotes, of course, but you can have quotes embedded in that as well. And does it have no quotes? Does it have proper quotation, or does it have improper, like one quote? Because that's going to throw off our number and cause a problem. Pardon me. And then within the pattern, are there spaces? Is there no spaces, one space, more spaces? Now for the file, what can we control? Well, for the file name, is it an existing file or is there no file with this name? Is the pattern in the file? How many times is the pattern found in the file? None, exactly once, more than once. And can the pattern be found more than once in any single line? Because maybe that's going to cause something to go wrong. And we'll say no more than one time on any single line, or maybe there's lines with more than one occurrence of that pattern. Right, so 6 things we can control. 2 of those have 2 options, 3 of those have 3 options, and then 1 of those has 4 options, right? And so the combination here is 108 possible test specifications to cover all the combinations. Not the worst thing we've ever seen, but again, more than you're going to write. So let's constrain that. And so let's narrow this down. Can we apply any error constraints? Well, for the pattern, if the pattern is empty, there's an error, right? If the pattern is longer than a line in the file, maybe that's going to be an error. If there's improper quoting, that's an error. If there's no file with the name, that's an error, right? So there's 4 of those already to eliminate this and eliminate combinations and bring this down. And 2 single ones we can apply. So exactly one time the pattern's in the file, that should work just fine, but we'll try it once to be sure. More than one occurrence of a pattern on the line should be fine, but we'll try it once to be sure. And that brings us down to 30, right? Much better from 108. Now, can we bring this down even further? Let's look at the if constraints, right? Well, maybe we'll look at this in terms of proper quotation. So if we make the choice that the pattern is proper quotation, well, then we're going to have spaces in the pattern. So if we choose this, then we could choose one space or several spaces, right? There can also be no spaces, but you're only going to have spaces if there's proper quoting around the pattern. Okay, so that's going to bring us down even further to 18 in the end. Does this make sense? Are there any questions on this technique? Okay. We don't have a horrific amount of time, but let's go ahead and take a 10-minute break. So let's resume at 2:27, okay? And come back then. And if you have any questions during the break, again, throw them into the chat and I'll address them. All right, let's go ahead and get back to it. Sorry for the somewhat shorter break. I just want to make sure we cover everything on time today and not keep you too long. So hopefully that was good enough. Again, feel free to keep asking questions in the chat as you have them. So our second technique is something called combinatorial interaction testing, and that's a fancy-ish name. But what it really means is that we're going to take the pool of test specifications, possibly filtered already using the last technique, and then try and from there identify a smaller pool of tests that cover all n-way, usually two-way feature interactions, right? So we'll choose two of those choices and look at all the different ways that we can cover pairs of those two choices. Right. So however you get your value classes for each choice, the next step in producing your test case specifications is in selecting combinations of values for those choices. The starting point, as we saw, was to exhaustively enumerate all possible combinations of values, but as we saw, the number of possible combinations explodes. Some methods, like the category partition method, take exhaustive enumeration as a base approach, to generating combinations, but allow the test designer to add constraints that limit the growth in the number of combinations. And this can be a reasonable approach when the constraints come naturally from your application domain, and eliminate many redundant combinations, like the error entries in category partition testing do. But it doesn't work if you lack real constraints. Like, it doesn't make sense to make up just random arbitrary constraints just to get the number down. So how do you know you got it right? Well, consider the set of features that control the appearance of our website here. We have here total of 5 choices we make. We have a different bandwidth modes, so it's a desktop site versus a mobile site versus a text-only version. What language is it displayed in? Is it in English, French, German, or Swedish? For our font choices, do we use standard fonts, only open source fonts, or a minimal set of fonts likely for bandwidth purposes? In terms of advertising, is it no advertising, targeted advertising, general, or minimal? And for screen size, is it displaying on a phone, a tablet, or full screen? Or sorry, full size, like laptop or desktop screen? Right? And so we have these choices we make when we're displaying our website. So you have different configurations of it. Exhaustively, if we tried every combination of these, we'd have 432 test specifications. And this is a case where it doesn't make as much sense to think about these in terms of error, single, or if. None of these should be giving you an error. They just might give you different appearances, and we want to make sure the different appearances look right, right? So what are the important ones to cover here? Well, 432 tests is more than we necessarily want to do, and we could hypothesize some constraints. But radical reductions would require adding a bunch of weird properties without any particular rationale. And so that's where category partition method breaks down and why it's more of a starting point than the end point. So what can we do with this, right? Well, when it is reasonable to expect potential interactions between features, but covering all combinations isn't practical, one reasonable alternative is to cover all k-way combinations, some value less than the full n-way combinations. So maybe usually 2 or 3, but we're going to really focus on all two-way interactions here. How much does generating possible pairs of values here and covering those pairs of values save compared with coming up with all combinations? Well, we've already seen the number of all combinations is the product of the number of values for every choice, and that this product grows exponentially with the number of choices. It turns out that the number of combinations that you need to cover all possible pairs of values grows only logarithmically with the number of choices. So it's an enormous savings in effort, right? So if we cover all pairs of choices here instead of all possible combinations of choices, rather than having 432 test cases we'd have to come up with, or 432 test recipes, we can now cover all these pairs in 16 tests instead, right? So that's much more doable than 432, right? So let's look at an example of how we do this. Let's say that we can control how we display paragraphs in a document. And we have three choices we make, 3 variation points, right? Our choice of those are line spacing, is it single, double, or multiple line spacing? Indentation, is indentation selected or unselected? And spacing between paragraphs, is that selected or unselected? Okay, so right, like I said, 3 choices, 2 values, 2 values, 3 values. That's 12 combinations in total. That's not too bad, but we can shrink this, right? So here's the enumerated list of all 12 possible configurations. And from each of those, you could create a large number of concrete test cases to check each of those different configurations. But instead of checking all of those, what we can do is we can try and look at only the two-way, the pairwise combinations. And that will reduce the total number of possible test suite configurations, right? So, what we can do is we can first look at all combinations of the values between line spacing and indent selection, right? So we have three choices for line spacing: single, multiple, double. We have 2 for the paragraph space, or not, sorry, for the indentation selected or not, right? And so we look at all the ways that we can combine those two: single and indent selected, single and indent unselected, multiple and indent selected, multiple and indent unselected, double and indent selected, double and indent unselected. Okay, so that's our starting point. Then next, what we're going to do is look at all combinations between indent selecting and paragraph selecting, and that's easy, right? Indent selected, paragraph selected, indent selected, paragraph unselected, indent unselected, paragraph selected, indent unselected, paragraph unselected. Okay. Right now, finally, we'll look at the combinations of values between line spacing and paragraph selection: single and selected, single and unselected, multiple selected, multiple unselected, double selected, double unselected. Okay. And now when you look at this separately, you'll notice a lot of these already overlap with each other. So we can now shrink this even further down. So by eliminating the configurations that repeat already tested pairwise combinations and some simple shuffling around, you can create an array of 6 different configurations that covers all pairwise combinations of inputs. So single selected, single unselected, multiple selected, multiple unselected, double selected, double unselected, selected and selected, selected and unselected. Where are we? Selected, right? Single and selected, single and unselected, multiple selected, multiple unselected, double, and so on, double selected, double unselected, right? So you can see all combinations of any 2 of these. And this is covered in 6 total test cases instead of 12. And eliminates a lot of fluff, right? So this could miss errors from the interactions between all 3 of them in a particular combination, but those are going to be very, very rare compared to errors between the interactions between 2 features, which this will cover all of, right? In a small example, it's not too difficult to create your pairwise, what we call the covering array, right? So this covering array is a set of configurations that covers all 2-way combinations here, right? In this small example, it wasn't too hard to create this pairwise covering array by hand, but when dealing with systems with thousands or hundreds of configurations, that's really hard, but this is not something we often do by hand. There's a bunch of tools that can do this automatically for us, including ones from like Microsoft, IBM, and others. They'll generate these covering arrays. In next class, we'll actually talk about a simple approach that you can also use to automate this. But for today, we're going to go through in some detail how you would do this yourself by hand, just to understand how this process works. So if we take a look at our website display again, and we start with just 3 variables, right? We can start with the bandwidth mode, the fonts, and the screen size. 3 of those, 3 values each, so in total 27 different combinations that you could get. But we can cover this in fewer, as we just saw, right? So we could start with bandwidth mode and fonts. And there's 9 ways that those can combine, right? Desktop site with standard, desktop site with open source, desktop with minimal, mobile standard, open source, and minimal, text only with standard, open source, and minimal, okay? So 9 tests can cover all combinations of these 2 variables, right? Now then, when we want to add the third parameter, screen size, Again, what we want to do is try and select values so that we achieve all combinations of screen size and bandwidth mode, which will again be 9. But also choose these in such a way that we also cover all combinations of font size and screen size, which would also be 9. But we can do this again with just 9 test cases instead of 9 times 9 times 9, right? Or 3 times 3, sorry. 3 times 3 times 3, so 27. So we can do this in 9 by just selecting carefully. So we cover all combinations of desktop site and phone, as well as standard and phone, desktop site with tablet, open source with tablet, desktop site with full size, minimal with full size, and then so on. So all combinations of any pair of these, of font and screen size, a font and bandwidth mode, a bandwidth mode and screen size. Does that make sense? Right? The key here is that each combination of 3 elements contains 3 pairs, and by carefully selecting values, we can make sure each combination covers up to 3 different pairs at once. So we can extend this to the full set. So we have 5 choices, 2 with 4 options and 3 with 3 options. In total, that's 432 combinations, but again, we can do this with far less, right? So again, let's start with 2 variables. And what you want to do is you want to start with the 2 that have the most options. So 2 of these have 4 options, right? So 16 to get all combinations of language and advertising, 4 times 4, right? So with 16 combinations, we can cover all of those. French and no advertising, French and targeted, French in general, French and minimal, German, and so on. Now we want to add a 3rd variable to this, okay? The rest all have 3 values, so we can pick any one of those. So we'll add bandwidth in. Now what we want to do is when we're selecting values for bandwidth, we want to look at each of these, English and targeted, English in general, and so on, and try to match these up in such a way that we don't have to add any additional test cases, and we cover all combinations of bandwidth with language and bandwidth with advertising. Unfortunately, we can do this quite easily, as there's only 3 options for bandwidth mode, right? So as we fill these in, we'll get a bunch of cases. Right now, these are noted with dashes. These are cases where we don't care what the value is. It could be any value for bandwidth mode. We've already covered within the 16 all the combinations of bandwidth mode with these other 2 variables. Right. Now, for later on, we might end up filling in some of these, but we can do this as we add more variables. So now we'll bring in a 4th variable, the fonts. And now again, as we go through and select, we want to select combinations of values of fonts. So we cover all combination of font with language, font with advertising, and font with bandwidth mode, right? And so again, we can do this. It gets a little harder as we go along to make sure we've covered every combination. But again, if you just look at this one at a time and try and hit each of those, it's pretty easy to do. And you still end up with some of these don't care values, right? Because you've already covered the other combinations, right? And then when we did this, we did have to go in and fill in one of those don't cares for the bandwidth mode. So if you go back here and then filled in, right? Oh, here it is. So we add in mobile site for this one just to cover one missing combination with fonts that we didn't have already. But we still have a bunch of these where we don't even care what the values are, and we're still within the 16. Right? So finally, we'll add this 5th one, the screen size. Right? And again, now we're choosing values for all combinations of screen size with language, screen size with advertising, screen size with bandwidth mode, and screen size with the fonts. Right? And here we don't need to set any more don't care values to get all the combinations in. So with 16 tests instead of 432, we'll cover all 2-way pairings. Now, if there are higher order interactions, if there's problems with one particular combination of all 5 of these, we might miss that. We might not have that in our magical set already. But this will cover 90, 95, 99, some huge percentage of the possible errors that can go wrong, right? The 2-way interactions are your most common source of problems, and those will be caught in this way. Does this make sense? Now, so far we've assumed all the combinations are legal. In many cases, not all values for all choices may be allowed. So before we apply this process, what we'll do is we're going to remove all those error or single cases like we identified before. And we can state constraints if we want before too, on addition of this, the omit certain combinations of values. So for example, on our website, it may indicate that text-only displays are limited to phone and tablet screen sizes. So you can't have a text-only display on a full-size display. And so we can note this here. We are going to omit at this any tests that have this particular combination of these two. Or for instance, minimal advertising might not be available on a full-size screen either. And so we're going to eliminate any combinations that have this pairing in them. Okay? So we can express these constraints as tuples with wildcards that match any possible value class. So we don't care about these three variables, but we do omit any to have this combination of full size and minimal, and that can be a larger too, right? We can note pairings between 3 or 4 or 5 of these that we're going to ignore and not allow in our list. So these patterns describe combinations that should be omitted from our list that we get in the end. So, right, for this previous example, we might specify constraints between text only and full size, or full size and minimal, or so on. This further reduces the number of test specifications, right? But it does make it harder to come up with the covering array because we're saying it's illegal to have these particular combinations. So make sure that it makes sense to have these in place. Don't omit something unless they actually are choices that are illegal to make at the same time. If you're doing this for a product line, you have your feature model already, though, and this tells you a lot about what you need to do. And like I said, next class we'll talk about a way you could program your own tool to perform this, but there's actually a bunch. Microsoft has one called Pairwise Independent Combinatorial Testing, or PICT, that does this. There's a list of tools in this pairwise.org/tools.asp. So if you ever want to do this automatically, you can try a tool for that purpose. Though you can also, as I said, next time we'll talk about how you can automate this even. All right, so we have a little bit of time left, and so we're going to do one more interactive exercise. And here we've got, we are designing system-level tests for a web browser with multiple configuration options, and you've extracted a total of 6 features, or sorry, a total of 6 choices. Do you allow content to load? Allow, restrict, or block are your values? Do you notify about pop-ups? Yes or no? Do you allow cookies? Allow, restrict, or block? Do you warn about add-ons? Do you warn about attack sites? Do you warn about forgeries, right? So you've got 6 different choices with 2 of 3 options, 4 of 2 options. That gives you 144 for the full set of test specifications. So for this activity, what I'd like you to do is create a covering, covering array. The set covering all the pairwise value combinations, all combinations of values for 2 of these. And I'd recommend you start right with the 2 variables with the most options. Allow content to load and allow cookies. Form all combinations of those, then add each of these additional ones one at a time until you cover all the different options. There's an activity, or for the full description, you can go to this bit.ly link, and I'll type it into the chat. But we got about 13 minutes left in class. Let's take 10 minutes and just start on this, and then I'll go over a solution, and then later on you can flesh this out and match it up and let us know if there's questions. All right, so at 57 after, we'll just briefly talk about a solution and wrap up. All right, let's go ahead and wrap this up. Again, I apologize. I didn't quite have the time to give a lot of time to each of these two activities today. So if you didn't finish either of them, I'd recommend that you sit down for a few minutes after class or when you have a little time and try them out and compare to the sample answers in the slides. Okay. Well, okay, so here we have this browser configuration where we're making we have six different variation points. We have for two of those 3 options that we choose from. For the rest, we have 2 options. And what we want to do is come up with a small set of test cases, much smaller than 144, that covers all pairs of these, or all values for all pairs of these different variation points, these different options we choose. All right, so what we'll do is again start with the 2 variables, the most values with 3 values, right? And come up with all combinations of those, and that's going to be 9 test cases. Allow content and allow cookies, allow content and restrict cookies, allow and block, restrict and allow, restrict and restrict, restrict and block, block and allow, block and restrict, block and block. Okay, great. Now what we need to do is add in a third variable, and we'll add in pop-ups. Pop-ups has 2 values, yes and no, and we want to cover all combinations of pop-ups with allow content and pop-ups with allow cookies and fill this in such a way we don't have to add any more test cases. And that's quite easy to do, right? So we have allow and yes, we have allow and no, restrict and yes, restrict and no, block and no, block and yes, okay? This also covers allow and yes, let's see, allow and no, restrict and yes, block and no, block and yes. And then we have 3 where so far we don't care about the value of pop-ups, so some of those might get filled in later on. Okay, now choose a 4th, add-ins, and let's add this in. Okay, so all combinations of add-ons with allow content, allow cookies, and pop-ups. So allow and yes, allow and no, restrict and no, restrict and yes, block and yes, block and no. For allow cookies, allow and yes, and allow and no, restrict and no, and restrict and yes, block and yes, block and no, and then of course yes and yes, no and no, and that's great. Okay. Okay, now we're going to add in another one. We add in attacks, and now we're going to cover all combinations of attacks and allow cook content, attacks and allow cookies, attacks and pop-ups, attacks and add-ons, right? And again, we can do this without adding any more test cases in. And then finally, forgeries is our last one, and that requires filling in a couple of these on the pop-ups, but still, we can do this within our 9 test cases, right? Does the idea make sense? Any questions on this? But this takes us from 144 test cases to cover all interactions down to 9 test cases, right? To cover all pairs. We might miss some interactions between 3 or 4 or 5 or so on of these, but that's going to be rare anyway. The real problems are generally going to be between 2 of these, and this will cover all ways that we can combine 2 of these features. Okay. So the process for deriving system-level test cases often results in too many test cases. And so 2 methods we can use to identify the important feature interactions and focus on those are category partition, the category partition method, where we use constraints to reduce the number down to eliminate unnecessary test cases, and combinatorial interaction testing, where we try and identify the important pairs of values. These techniques are complementary, right? There's a question here. Will there always be n by m, or do we sometimes have to add more rows? And the answer is we do sometimes have to add more rows. Sometimes you're not going to be able to, especially if there's constraints between variables. And if there's a lot of variables, you often will need to add some more. So for these examples, we were always able to do it. But as you add more choices that you make, you often end up having to add some more rows. But it's an additive process as you go, right? So when you see you can't make this combination, you throw in one more and see if you can then. And so it doesn't tend to grow by too much. But often you do have to add a few, especially if you have constraints, because if you have constraints, it becomes much harder, right? And all of our examples had no constraints so far. But if there are ones, that's going to typically add a few more test cases. Okay. And like I said, these methods are complementary. So you could start with the category partition method and then select the n-way interactions or the two-way interactions from what's left. And that's not unusual. Or you could just use one or the other. Next time we're going to talk about automated test case generation. This is getting a little more researchy, but this is what's known as fuzzing. It's often used to generate test cases to identify security risks and buffer overruns. Right, but this is a way to automatically come up with test cases. And we'll talk about how these same techniques can also be used to automate things like combinatorial interaction testing. Assignment 4 is out. Take a look at that. Get started on that. If you haven't, it's due December 20th. Just quickly before we go, we'll have assignment 5 out so you can see it shortly. It's going to be due after the holidays on January 10th. It's not going to be too massive, right? But you're going to have a while to do it just because there are the holidays in there. We don't want you to work too hard over the holidays. So it'll be out soon so you can start looking at it, but it won't be insanely massive. The individual assignment will have full details out on that shortly, but to give you an idea, it's going to be similar in style to a take-home exam. It will be assigned and submitted. Right now we're looking at January 13th. But roughly sometime in the week of January 11th, there will be you'll be given this. You'll be given a while to work on it, so it won't conflict with any one exam you have for another class. But it'll be basically a long take-home exam. You're expected to work on individually with more open-ended questions based on the lecture content, a little more theoretical than the assignments. And like I said, we'll have more information on that soon. But you can expect it to be similar to an exam and take about the same amount of time you would put into an exam. If there's any questions, let me know. Otherwise, that's all for today, and I'll see you next Tuesday.